All right, so welcome back. Welcome back to the channel. So, yeah, I took a little break after doing the part one of this series. So we are back. This is part two of zero to LLM expert. So in this video or in this part, we are going to learn a few. We are going to go into a little depth of deep learning, what it means, and also we're going to cover all the main part. I think so this video, we are going to cover all the main part, the main language models that has been used, the like core, the core performance or the performer of a language model is the model, the background deep learning model that has been trained. So we'll be learning about that model. We'll be looking at different approaches to this problem of language modeling, right? And after that, finally, we are going to get to transformer, which is the architecture that is used in the current LLMs. So in the current LLMs, transformer is used. Now GPT refers to generative pre-trained transformer. So that's also a transformer. We're going to understand the architecture of a transformer after that. So basically, I'm going to go to everything pretty fastly. So in the last video, we have learned about word embeddings. And we have learned about word embeddings. So I'll just cover. I'll just review them what they are. Word embeddings. Let's just do a quick review of what word embeddings are. So basically, each word. So there will be each word. We'll have many words, right? So in order to represent a word using a numerical matrix, we'll use this word embeddings, and this numerical matrix through which we will represent this word. The numerical matrix will carry some information about that a specific word. So if we were to plot the words based on that numerical matrices, um, you know closer words will have will be in closer positions. For example, the word cat will be closer to the word dog, right? The distance between cat and dog will be closer if we trained a good embedding. So basically, our goal is to make similar values closer to each other or similar vectors closer to each other, similar word vectors. So each word will be represented by a vector. So that's the main idea of word embedding. We have looked at how we train that. We also learned about, we have also covered, I think, neural networks in that. So basically, we'll be having some so let's say we'll be having a sentence, maybe in the training data. We're going to have the training data, right? We're going to, let's say we have a sentence called I am I am angry, something like that. So basically what we'll be doing is in the training phase, let's say this is the training data. So in order to train the embeddings, not the model, in order to train the embeddings, basically we'll just get this angry out. We'll just remove this word angry, and basically we pass this I and M to an equation. So basically, yeah, I mean, will be having some neural networks. Let's say it will be creating this architecture in which the word I is first going to be represented by a tokenizer. So tokenizer is nothing but or just some number, right? I is going to be represented by a number, right? A basic random number. So each for every word in the dictionary, a number will be assigned. So the model will assign number. So let's say this word I, let's say, so the numbers are pretty random. So let's say randomly I'll say 9. Here, let's say I am is, let's say, 1000 or anything like that. So basically we'll pass this values, and uh, the final is going to be an output. So basically we'll have something called weights here, right? We have something called weights, which are just something like that. So let's say W times X, right? And here also W times X. So basically this is called a weight, for which we are going to multiply weight by the input. Here input is X, so X input is denoted by X. So basically we multiply, or there is some kind of function between these double weights and in the input. So we'll basically do this. I'll cover what these W's are, right? I have covered, so this is just a review. So basically this output, we're going to predict an output, right? We're going to predict an output, let's say a number. We want to make sure, right? We want to make sure that this number is equal to the token value of angry, right? So this is 9 is the token value of I. So basically we'll be trying to predict the token value of angry. So let's say the angry, for angry, the token value is 23. So we'll be trying to predict the word 23. And in order to do that, we'll have something called loss function. So this loss function, so the model's main goal is to decrease this loss function. And if the output of the model, let's say the output of the model, which is O, is equal to 23, right? If the model predicts the correct word, the loss function will be lower, and that is what the model wants. And if the model does not predict, the loss function will be higher. So basically, the model will try to reduce the loss function. In order to do that, the model will update these parameters W's. The model will try to update these W's such that the model such that the word angry is predicted simply, right? And then we'll basically update this using derivatives. So we basically will calculate derivatives. We'll be doing that. So we have a specific loss function called cross entropy, categorical cross entropy, which I think is not so important. The main thing is, we're still in the word embeddings. So the main thing is how these words are represented, and this I would basically at this I. So each connection here, each line here associates with some weights. Let's say this is W1, W11, W12, this connection, and let's say this connection is W21, and this connection is W22. So I will be equal to this vector W11 and W12, right? W11 and W12 I, and and M here will be W21 and W22 simply, right? And we'll update this embedding such that the meaning is represented. And we also have word to vec, which is now taking angry and predicting other words also. So that is the word embeddings. That's the idea of word embeddings. And basically, this is neural network. Now you also have, this essentially is a neural network, what a neural network actually is. So one thing, let me just cover language models. So we'll get into the actual topic of this video, language modeling, how to model data, how to model language data, how to make the model understand language data, and let's say do a specific task, right, of predicting the next word. So in LLMs, normally in LLMs, so there is this field of NLP. NLP involves different tasks, right, for machine learning models. So in NLP, right, I'll just go through NLP first. So inside NLP, we have many tasks. For example, we have text classification tasks. So text classification is actually pretty simple. I mean, you could understand it with the knowledge that you have of neural networks until now, if you have stayed with me. So basically, we'll take a word. So let's say there is a sentence. So let's say our goal is to predict if a sentence is, let's say, positive or negative. I mean, if it is spreading hate or positive things. So let's say I like this. So let's say I say something like this. I like this product. So let's say this is an Amazon review. I like this product. So basically, this is a positive review, and we'll be given some data which the model will train on. So let's say for this task of positive negative classification, we'll be giving some training data. In this training data, this training data is going to consist of many pairs of text and the sentiment. For example, we're going to have data like this. So let's say I like it, and let's say the sentiment is going to be 1, saying that it is positive. And let's say there is another thing saying that I don't like it, I hate it. It's going to be 0, right? Something like that. Like binary classification, it is called zeros and ones. 0 refers to negative, 1 refers to positive. So we're going to have this training data, and the goal of the model is the goal of the engineer is to train a model that such that the model could understand whether a comment or a review is positive or negative. It may be for further analysis of a product or something. So here in the training phase, while training this model, so we'll be having this data, and we'll pass all this data into a neural network, and the neural network will predict an output, right? This O. And the loss function, we'll be having a loss function, and there'll be weights here. Just like I've discussed here, there'll be weights in which we'll just multiply the weights and I'm going to share another architecture of neural network. Just a minute, don't worry. So this is the classic neural network. I just think this as something like ANN or something. Just as classic neural network, let's say. I'm going to cover another architecture for language modeling, which is RNN. which we'll cover in just a minute. So we'll be having loss function, just like all you know, just like you know, and we're going to use something called binary cross entropy. Whenever we are doing like binary classification, we use binary cross entropy. So if the model predicts correctly, if the model predicts 1 and the actual answer is 1, the loss function will be lower. If the model predicts wrongly, for example, if the model predicts 1 and the actual answer is 0, it'll be given higher loss function, which the model doesn't want. So basically, we'll be having a loss function, and we'll train the model. We'll train the weights such that the model predicts, let's say, 1 for this. Right? The output should be 1, right? Because I like this product, is a positive review. And remember, this data is already in the training data, right? This data and this data is all in training data. So this is as the output of the model is commonly denoted by y hat, the output of the model, and this is denoted by x. So we're taking yx and predict y hat, and the model and the actual value is called y, right? So I'm going to just some notational things here. So this is y, the actual data that is in the training data. The training data consists of answers and questions, right? The training data consists of reviews and their sentiment, right? And basically we'll train the loss function such that the weights are updated. And after updating the weights for all these sentences, after doing this for all sentences, updating weights for all sentences, we'll be getting a perfect model which could detect sentiment of any text. So that is sentiment analysis, just a basic maybe a just a analysis of a project that we could do using NLP. Congratulations! Now you have successfully learned about neural networks in a basic way. So remember, this is we'll be not passing the actual sentences. We'll be passing all this text into word embeddings. The word embeddings will convert each word into a vector, right? The vector consists of the weights. Already covered it in this video, also covered it. So we'll be having that. We'll be passing all these vectors as the inputs, and we'll like do all the calculations in the neural networks. So that is the basic idea. And now let's look at a problem, right? I mean, this neural network is perfectly fine, right? The neural network is perfectly fine, but still, right? Performance, performance wise, it will not perform very good in the especially in the field of NLP, because word is because sentences are sequential. I'll just cover what that means. Sorry for that. So yeah, sentences are sequential. They have sequential data, something that progresses. I mean, like let me just give you an example. Let's say let me just give you an example. Like just let me for example, ಏನಪ್ಪ all right, sorry for that. So I have this I have found this example why word order matters. So that's just an example so that you can understand. So we have two sentences. I have to read this book, and then that's the first sentence, and the second sentence is I have this book to read. So basically, just you can understand the difference, right? I have to read this book is a responsibility. The person have to read that book just like a responsibility. Whereas in the second case, it is not a responsibility, but it is looked as a burden. I have this book to read. I mean, like the word order definitely matters here. And if you think about neural networks, there is no capture. Really the order is not being captured. For example, we have let's say word 1. I'm not good at words, so basically I'll not be giving many examples, and that is a very bad thing, right? So basically in a LLM, so I want to revise again. So this is an NLP problem. Sentiment analysis is an NLP problem. So the only difference between NLP and LLMs, in LLMs, The main goal is to predict the next word. So remember, throughout this video and throughout your whole life, whenever you think of LLM, just this is the main goal. This is going to be the main goal of an LLM, to predict the next word, right? In the sentiment analysis case, the goal is to predict the sentiment, right? The goal is to predict the output. But here in LLM, an LLM, large language model, the goal is to predict the next word given the previous words, or may predict the middle word based on the surrounding words, right? In the training phase, this is the main thing. Even ChatGPT does that. Even ChatGPT, the model just predicts the next word based on the previous words. So this is the main function, and the loss function is also common for every LLM. For every LLM, the loss function is this categorical cross entropy for every LLM. So basically, categorical cross entropy is that if the correct word is predicted, then higher reward or lesser loss function. So if correct word is predicted, lesser loss function. If correct word is not predicted, then higher loss function. Simple, right? That is the thing, right? For every LLM. So therefore, if we use a neural network for training an LLM, this is what's going to happen, right? So let's say word 1, word 2, word 3 are given to a neural network, classic neural network. Let's say A and N. I'm going to represent the classic neural network that I have learned as A and N, and the goal of the model is to predict word 4. The model should predict word 4, and the model's main goal is not just predict the word 4, because the word 4 is already in the dictionary, or sorry, in the training data. The word 4 is already in the training data. The training data consists of word 1, word 2, word 3, word 4, the whole sentence. The model needs to understand the relations, right? The relations between, let's say, word 1, word 2, word 3, and word 4. So basically, this is the main goal of the model. And relation will be captured. But here, if you use an actual neural network, a normal neural network, relations will be captured. The model would perform very well. The model would be very well trained. But here, word order. All right. So yeah. So this is a neural network, a classic neural network. But the problem is that word order doesn't matter. So word order will not be taken into account. And for example, if you were to give maybe the words in a jumbled form, let's say word 3, word 1, word 2, and maybe give this maybe inputs in neural network, the model would basically consider all these, both of these sentences to be the same. That is what the model would conclude. This is what the model will conclude, which is definitely not good, right? For just this maybe example, I have to read this book is very different from I have this book to read. One sentence shows responsibility, whereas other shows some casualty. Definitely the words are not similar. The sentences are not similar. It's therefore, and using a classic neural network that we have learned now doesn't work, because it doesn't capture sequential manner or sequential relations. For example, I have let's look at a situation. Let's look at a problem called stock price prediction. In the case of stock price predictions, let's say I plot a graph. Let's say something like this. So let's say this is a stock of a company, a pretty good company, I think. The stock price is not something that is stable, but something that is changing. So if you think about it, the stock data, this is the stock data, right? And the sentences and language, for example, it's I am Joel. Both of these are pretty similar, right? These are sequential data. These are called sequential data. The stock price data. So let's say this point, the stock price at this point, let's say, depends on the previous points, right? The previous points will help us to give, will just hint us to predict the current stock price or the future stock price. So based on the previous stock prices, we can predict the next stock price. Similarly, in language also, the current word will have some some relations between the with the previous words. So therefore, stock price also is stock price prediction also is somewhat related to language model. That is what I wanted to tell. So what is what is this new architecture that we have to use to solve this problem? That is a problem here, right? uh, Neural network does not work. I mean, it I think it's also been shown experimentally. I mean, there has been many experiments now. Even I have used neural network for doing NLP tasks, but it doesn't work. It just doesn't work because sequential data or sequential relations are not captured. When let's say two words will be closer to each other, for example, I and am, we can be sure that almost all the times I and am will be closer to each other, not just appear in sentence but also closer to each other. That is one relation that is only maybe captured with sequential models. So what are sequential models? Sequential models are models that are used to understand sequential data. Right? Sequential models are models that are used to understand sequential data, something that changes over time. Right? Something that maybe the future inputs, future outputs depend on the previous outputs. So that is the thing. Just like stock data. In stock data, we take the previous outputs and predict the next line, continue the line of stock price. In language also, use the previous words and try to predict the next word. In ChatGPT, for example, the previous words will be the question and the future words will be the answer. So basically, I will have a huge string in which the question will be inserted for first. The model will take that question as the input, and the model will try to add in the next words slowly, right? One at a time. So what are sequential models? So I'll just explain the architecture for RNN, and basically we'll look at LSTM GRUs in lesser detail. So in RNNs, we'll be having this architecture, which I'll share. For example, we have a sentence. I am a Joel. I am Joel. I am a Joel. I am Joel. I play cricket. Let's say we have the sentence. So basically, we have this. I'll just draw the architecture. I mean, drawing is the thing. So basically, we'll have a, let's say this is the block. This is the block. So if we want to predict the next word, right? We'll basically have this architecture. So this will be x1, x2, something that is belongs to time, x3, and so on after the last output xn. And this will be the final word, which is, let's say, which should be cricket, right? Which should be cricket, or it's a y hat. So in this question, in this thing of predicting the next word, taking the previous words, let's say I delete this word cricket. I delete it from the word. So I will pass in. So I will be x1, am would be x2, Joel would be x3, comma, and I mean maybe not comma. I mean, we could put comma also with some word embeddings. We'll take all these values. Play would be the right final thing, and we'll try to predict cricket. So we'll match. We'll try to find. We'll use the loss function. Y is cricket. Y hat is y hat. The output of the model, and this is the architecture, right? Simple, pretty simple, right? So one thing that I want you to keep in mind is that we'll be using a neural network here. We'll be using a neural network here. Sorry. Right, we'll be using a neural network here. Neural network. Why is everything bad? Right. 1 second, please. All right. So yeah, I'm back. Yeah. Hopefully it works now. So we'll be using a neural network now. Everything. So each block is essentially a neural network, a simple neural network. I'll tell you. And basically, 1 second. All right. I'm sorry for that pause also. I'm sorry for that pause. Yeah, let's continue back. So basically, we'll use a neural network, right? So here, rather than the one thing that I want to observe here. So basically, one more note here. So all these neural networks are basically the same. When I say all these neural networks are the same, I mean all the weights of the neural network. The weights of all these neural network is going to be the same, right? So the output of this neural network, that will be having this output of the neural network. The output of this neural network will be the second input of this neural network. Right? Remember, this neural network will not have any input, or maybe some input that is maybe 0 or something. Um, and the and basically we'll be taking one neural network, only one neural network, and just copy it copy it and just flatten it out into this architecture. Rather than having this neural network, rather than this architecture in the classic neural network, we'll be passing x1, x2, x3, and xn up to xn. We'll be passing all these values into the network at the same time and try to predict the word predict y hat, and we'll try to get y hat closer to y. So basically, rather than doing that, we'll be having this neural network taking x1 separately and do some calculations on x1, try to understand what x1 is, and have some weights not associated with x1. The weights will be common to all. The weights also, the weight updation also will be common to every. No, for example, x1 is given. We'll be having some weights. The same weights will be for here, here, here also. So basically, we'll be having this. We'll be having some weights, right? Using the weights, we'll be having some calculations. Maybe here we'll have w wh into x1 would be the output of this model. Maybe y1 y1 will be passed here. We'll be passing y1 to this thing. Here we'll here also we'll be having wh only, right? Wh is common. Wh is common, and basically we'll be doing into x2, which will be y2, and we'll be basically doing that for all these things, and the final output would be y hat. Right? Try to the last word. Yeah, that is the basic thing, the basic idea of the model of how we do this. Whenever we want to like predict the next word. In the case of predicting the next word, we can use this simple architecture. And I think we have we could have also I think another architecture also, like based on the problem. For example, maybe maybe you want to do maybe Google translation or some translation task. If you want to, let's say, do a translation task, maybe train a model for doing translation tasks, you could have something architecture like this, right? We could have an NN, which takes in our input x1 and try to predict y1 for that word, or or something like that, or not even this, right? Let me just introduce another architecture, seek to seek architecture, NN x2, and maybe we have three words, let's say x3, and maybe we have only two words in the translated language, or maybe in language like Telugu or something. Maybe we only have two words, y2. So this architecture can also be employed, right? Here we have three words in English and two words in the output, or Telugu, two words in Telugu. So x1, x2, x3 are English words, and y1 or y hat 1, y hat 2, more precisely, will be the words in Telugu. In training data, we'll have this data of English and Telugu translations, and we'll basically pass them through the neural network and try to update the gradients, update the weights. So how weights are updated here? So basically, let me just share with you how weights are updated. Here in this case, we'll be calculating loss function, right? We'll be calculating dw with respect to, or dwh with respect to loss function, right? For this, like maybe for the final output. So we'll be calculating y hat, like how we will be calculating loss function with respect to y hat, and after doing that, we'll basically update the values, right? We'll basically calculate this. after calculating the output, we'll calculate dwh with respect. So we'll be calculating how weights. We're not only calculating how wh how wh influences the output, but also how wh influences the previous wh, right, or the previous output. We'll also calculating that. And let me just go through and just give you some formulas just so you can remember everything. Yeah, this formula, this I think is pretty nice. So here all the w's, b's are also there. B's is b, I think you could easily neglect the b's. By ba, you could neglect the b's. So they are also like weights which we add. We multiply the inputs by w and add weights, b's. Just you can just forget that. In this architecture, we'll be taking 80 minus 1, which is the previous word. We'll be multiplying that by WAA, right? And then we basically have some calculations. We'll be taking the current input, and multiply that by WAX. So that is also there. So now we'll be taking here, right? We'll be also taking like WX H into X2 plus WY into the previous output, which is Y1. If I forgot to add in here. So we'll here also we'll having WH into X3 in this for this neuron plus WY, let's say another weight multiplied by the previous output, which is the Y2. And of the previous output or the previous hidden state, which is also called, we'll be taking into that. We'll be taking that also into account, and basically we'll be calculating derivatives. So basically, this weights will be calculating the derivative of loss function. Here we'll be multiplying this using the chain rule essentially. We're multiplying this by the influence that this weights has on the output of this weight or something like that. I know how WH has outputs on Y3 and how it has on Y4. Y4 is YN is the output, final output. So yeah, I think hopefully you got it. We have this architecture. The main takeaway is that we are going to have this new architecture in which sequential data will be valued, right? In which we're going to roll out this neural network. All this neural network are going to be the same. All these boxes have the same neural network, same weights. We're passing the X1s, X2s, X3, Xns, and we're going to predict the last word, right? The last word from the last neural network. That is the thing. But there is also one more problem from this RNNs. So we have one problem. The problem with RNNs. The problem is vanishing gradients. I'll just explain what that is in very detail. Vanishing gradients. So the thing is, the model could not remember things. For example, on the internet we have sentences with like large number of words, right? There are very large sentences. So basically, maybe some previous words will be forgotten. For example, let's say Joel is a boy who likes playing cricket. Let's say we have a sentence. I'm just going to give an example, very brief example, and maybe we have a fill in the blank here, and maybe we want to fill it with an adjective, whether he's a he or a she. I mean, as a human, you could easily say that is a he, and because the sentence is also very small. But let's say we have other things here, maybe other details. Let's say this is a large sentence, and the model might forget. The thing is, the model might forget that Joel is a boy. Right? That priority will not be given. So basically, the model. So this is actually called hallucination. It occurs a lot in language models. I mean, when I say a lot, I mean a lot. So basically, it might forget different important details. And because RNNs, if you think about RNNs, this output, let's say Y1, will have very, very small. So Y1 will have very, very small influence on Y hat. So Y1 will not play a huge influence on Y hat because if you think about it, this y1 will also be a factor in the output, but also we're having a multiple calculations here, right? In the middle, we have multiple other words and multiple other weights are calculated, multiple other y's are calculated, which makes y1 to have lesser influence on y hat. Right? That is one thing. That is one problem with RNNs. And that is what LSTMs and GRUs solve. So using LSTMs and GRUs, you could solve this problem of validation gradients. So basically, I just cover that or all that means. So I'll just get the formulas. LSTM formula. I don't be intimidated by the formulas, but they're pretty straightforward. I think. So yeah, this is the formula of LSTMs. So here, let's say here in this case we have xt, which is the current input state. So we'll remember basically in LSTMs also consists of the same architecture, right? We're going to have the cells lined up, which contains of a neural network. We got x1, x2 up to xt, and we're going to like predict the next word y hat or something like that. Right here, right. So yeah, so here xt, you could see xt, right? And also you could see w's. I think you are familiar with xt's and w's here, right? And then ht minus 1. ht minus 1 is nothing but this. For example, we want to predict this. So this is going to be x1. This is going to be h2, h1, h2, h3, so on. So basically, ht minus 1 is the previous input. For example, if we take in this neural network, this cell, ht minus 1 will be this thing. xt would be this, right? And then ht would be this, right? This is ht, this is ht minus 1 for this cell, right? For this cell, ht minus 1 is this and ht is this. Let's say we'll take in this cell. Let's say maybe we zoom into that. And these are all the calculations that has to be done, right? What are the variables that we can see here? Number one, you could see is the sigmoid function. Sigmoid function. I mean sigmoid function. Whenever you use a sigmoid function in machine learning, we are doing something called binary classification. So this is sigma. This small function. So that is sigmoid function in which just numbers will be converted into zeros and ones. Right? For example, when you are doing multi-class classification, when you have a large number, when you want to convert it into zeros and ones, either 0 or 1, you use the sigmoid function. That is it. And here, basically, we'll have multiple weights. We have multiple weights. So here, u also is weights. U here, just like w, we also have u. Just to add more complexity to the model, we'll be using u's. And when we multiply xt's, right? We'll multiply the current inputs. We'll multiply xt's, the current inputs, by u's, this weight, and we're adding ht minus 1, the previous weights. We'll be taking the previous weights and multiplying that by wi. And here, as you can see here, we have it, ft, ot. So these are called gates. So gates help in control of passing of data. So basically, in an LLM or in this LSTM, will be so basically the only difference between RN and LSTM is that in LSTM we're going to have multiple gates, and these gates are going to control which information is going to pass and which information is going to the model is going to forget, right? For example, we have a large sentence, very large sentence, and there is one important word. Let's say in this case, in this example, boy is a very important word. In order to predict this word, boy is very important. So basically, the model in the LSTM, the gates should figure out that the word boy is more important than other words, right? Let's say a, boy is more important than a, maybe for this word, predicting this word. So that is the main function of LSTMs. Here, I have these multiple weights which are going to be updated in the phase of model training. In the phase of model training, when the weights are going to be updated using loss function, these weights u's and w's are going to be updated. right? We're going to taking the previous outputs, previous hidden states, multiply that by wi, wf, wo. Remember, these are different. Wi is different from wf, wf is different from wo, and etc. And also wui, uf, uo also. We can have that also. And we're actually going to multiply all them. We're going to multiply all of them. And basically, I, f, and o are going to be zeros or ones. I is going to essentially going to be a 0 or a 1. F is also going to be a 0 or a 1. O is also going to be a 0 or 1. And the only factor that is going to determine whether this I, f, and o are going to be zeros or not are these weights. So the weight is going to control whether the gate should be open or not. That is pretty, I think that is very intuitive, right? So W and U, for example, Wi and Ui are going to control whether I is going to be 0 or 1. And in the same way, WF and UF are going to control whether FT is going to be open or close, or 0 or 1. And in the same way, UO and WO are going to determine whether OT gate is going to be open or not, or 0 or 1. So yeah, we have these other variables that are going to control whether it's going to be 0 or 1. And yeah, so that just keep that in mind. And in the next formula, C, I don't know what that is, maybe C hat T is going to be the tan h of xt ug plus ht minus 1 wj. Just another, that's the same thing, but here we have ug, which is another weight. wg is also another weight, and xt and ht or ht minus 1 are going to remain the same in all the formulas. After doing that, in the final, this ct is going to be the maybe hidden state. So here they have two, ct and ht. In our case, in the case of LLMs, will be not needing that. We only need either one. Or what you could do is you can just remove the ct, right? Maybe ct is not required as the output, or maybe you can just use it. I mean, I think we could like remove the ht. I mean, removing ht would cause trouble to this. So yeah, I mean, similar architecture, let's say. So here in this, while calculating ct, right, we'll be having another sigmoid function, which is also going to be a 0 or 1 thing. At ct is also going to be either 0 or 1. Okay, ct is going to be either 0 or 1 sigmoid function. And here we have ft, right? We have ft, which is going to be this. So we're going to have ft, which is this gate. So ft is also going to be 0 or 1. And we're going to determine whether the previous output ct minus 1. Ct minus 1 is the ct of the previous one. So we're going to have cell state. Right, each neural network is going to have a ct, ht also, and all the other things. So this is going to be ct minus 1, ht minus 1. This is going to be, with respect to this, I'm talking. This is going to be ct, ht. This is going to be ct minus 1, the previous one. This is going to be ct plus 1, right? This is going to be ht plus 1, and so on, plus 2 or something. So basically, we'll be taking this previous cell state that is also calculated. If this cell is the first cell, then maybe we'll not be taking the CTs, but we'll be taking the previous cell state, the previous CT minus 1, right? The previous cell state that has been calculated, and we'll so this FT, the forget gate, will control whether CT minus 1, the previous output or the previous word, is important or not, right? If we'll just the model will determine whether the previous input previous word is important or not. So if ft is maybe closer to 1, if ft is closer to 1, then more importance will be given to the previous word, right? If ft is less than 1 or very smaller, then ct minus 1 will be given lesser importance. And if you could see here, in a very intuitive sense, maybe there is one word way back in the sentence. So this importance of maybe this word is important, then this importance will be carried out throughout all the cells, right? All the cells will carry the same importance for that word, right? Because maybe in each cell we are going to give some importance to the previous word. And so basically, if a word is very, very important, then the importance would be carried on until the the last word, right? If the word is very important, then it will be carried out, because CT minus 1. So each cell will have a previous cell. Each word will have a previous word, right? And that importance of the word will be carried out throughout all the cells, and in the same way, right? So we're going to determine whether we are going to we are going to give importance to the previous cell or not, and then we're going to add that with the I get times CT, the current CT. So we're going to, it's just going to be this thing. So basically, we will be determining whether we have to give importance to the previous word, and then also we're going to determine how important this is the current word. We'll be both doing that, and we're going to add these values. And again, this is also going to be inside a sigmoid function. That is, it is going to be, the output is going to be 0 or 1, right? After doing this, just after doing this, so basically, we're going to get the previous word, the importance of the previous word, the importance of the current word. We're going to determine whether the current word is more important than the previous word, right? Or how important is the current word and how important is the previous word, and we'll be carrying the most important words, right? Maybe in throughout the history, or throughout the loop of looping through all the words, through looping through all the cells, some words will be important, and if that word is important, and if the model is trained right, the importance will be carried out throughout the model. And in the final HT would just be a tanness function, and we're going to multiply that by OT, which is just another gate, which is going to control how much bigger or how much smaller the output should be. Pretty simple, right? You could ignore the tanness functions. They're just like converting the outputs into like this 1 and -1 range or something. Yeah, 1 and -1 range. That is tan H. I mean, that's it. And that's it. This is the function of LSTMs, long short-term memory. So basically, we'll have some gates that is going to control whether some information is going to go through the process, whether some word is important or not in the history. And as we go on, some words will be given higher importance and some words will be given lower importance. And every word definitely would carry some importance further, right? Based on how useful that word is. That is LSTMs. That is the basic LSTMs and RNNs. I think I'm going to stop this video here. I mean, I really plan to cover transformers also, but I think that is very bad. That is very, that is not very good. I mean, it might take a lot of time. So therefore, I'm going to stop it here. I'm going to stop everything here. LSTMs and RNNs. We have covered both of these architectures. Hopefully, you got everything, understood everything. If you didn't, please comment. I'll try to maybe reply you, or maybe create another video. I definitely could create another video because I'm free. So yeah, that's it for this video, and I will see you in the next one. So yeah.